Good morning. So let's just give a short amount of time for people to show up and then we can start. Okay, so while you're waiting just a short amount of time, think about what questions you want to ask me about the homework that was due today, homework 4, right? So I assigned all of homework 4 to be due today. All right, and keep in mind that the sections that are going to be on test 1 are the sections that that are chapter 3, right? So these 3 sections are the 3 sections that are going to be on test 1, right? The other questions are test 2 material. Okay. I'm willing to open the floor again to this homework assignment for chapter 4 after the exam. So if you want to focus on chapter 3 questions, but you still have questions from homework 4 about chapter 4 questions, I'll reopen the floor for more questions about chapter 4 after the exam on Thursday. Okay. So I would rather focus on only the chapter 3 questions from the homework, but the whole thing was due. So let's see. Okay. Let's start. So anyone have any questions about 3.3.2, 3.4, or 3.5? Any questions? So I prefer the questions out loud, but okay, 3.4 number 1. So this question. Okay, so we're looking at this one. So 3 boxes have identical exteriors. Box 1 contains 2 pennies, box 2 contains 2 nickels, and box 3 contains a penny and a nickel. A box is selected at random, and a coin is selected at random from the box. If the coin selected is a penny, what is the probability the other coin in the box is also a penny? Okay. So let me copy this. Let's see here. Yeah, very good. Okay, so that should be copied. I'm going to go to the whiteboard and paste it here. Okay, so this is a question you asked about. All right, I guess that'll do. Okay, so 3 boxes have identical exteriors. So I'm going to use brown for the 3 boxes. So we have box 1. We have box 2. And we have box 3. I haven't left myself much room to do something else. Okay, so those 3 boxes. Box 1 has 2 pennies. So 1 penny. 2 pennies. Box 2 is 2 nickels. So a nickel I'm going to choose here. That's a nickel. That's a nickel. And box 3 contains a penny and a nickel. So here's a nickel and also a penny. Okay, so let's check to make sure we got it right. 3 boxes have identical exteriors with brown lines on the outside. Box 1 is 2 pennies. Box 2 is 2 nickels. Box 3 contains a penny and a nickel. A box is selected at random and a coin is selected at random from the box. If the coin is selected as a penny, what is the probability that the other coin in the box is also a penny? Okay, so we're looking at 2 events here. So let's so it says if the coin selected is a penny. So I'm going to make this an event, and I'm going to call this event. I'm going to call this event P. Actually, I'll call this event A. Let's call this B, okay, for reasons you'll see later. And then I have another event. What is the probability that the other coin in the box is also a penny? I'm going to call that event A. And so the question is to find the probability. We want to find the probability of one event given another event, right? It's a conditional probability. So after if is the given event, if the coin selected is a penny. So this is the given event, B. And it says, what is the probability that the other coin in the box is also a penny? And so that's event A. So it's probability of A given B. That's what you have to find, okay? So that's the goal. The goal is to find the probability of A given B. That's the goal. Okay, so the goal is to find the probability of A given B. Okay, and so the probability of A given B is the probability of A and B divided by the probability of B. This is also the same as the number of elements in the event A and B divided by the number of elements in the event B. Okay, because the denominator is going to cancel. The numerator and denominator are each fractions, and the denominators cancel. So why put the work in to calculate the denominators? They're going to cancel anyway. So you want to find the number of elements in A and B and divide it by the number of elements in B. So let's look at A and B. B is you select a penny, right? And it's asking what's the probability the other coin in the box is also a penny. So only box 1 is in event B, right? Event B, it has to be this box, right? So, so you're selecting one box at random, but there's only one box in which you can select a penny, and the other coin in the box is also a penny. So, so there's one way to do that. NAB is the number of boxes in which that could happen, right? So you have 3 choices for a box, but you can only choose. There's only one box in which you could select a coin, and that's a penny, and the other coin is also a penny. So NAB is 1. And then you divide it by NB. NB, B is that the coin selected is a penny. Okay. So okay, so there are actually, sorry. Let me do this. Let me keep it as the probability. That way I don't just, there we go. Just need to erase this without erasing everything else. There we go. Nope. Sorry. Okay, so, all right, so we want to find PAB over PB. So the probability of A and B is, okay, so if a box is selected at random, then a coin is selected at random from the box. Okay, so the probability of AB right? The probability of AB. Okay, so there's 6. So if you choose a box and a coin from the box, right? You got to choose this coin in box 1, or this coin in box 1, or this coin in box 2, or this coin in box 2, right? So you're selecting one coin. So there are 6 possible coins to choose from, and then A and B would be, you know, one of these 2 pennies, because those 2 pennies are the only pennies you could choose in which the other penny in the box is also a penny. So P of AB is 2 6. Okay. P of B is the event is the coin is a penny, right? So you actually have 3 choices of penny, 1, 2, 3, out of the total 6 coins that you could choose from. So you have 3 over 6. So that's 2 over 6 over 3 over 6. And this is equal to 2/3. There we go. Okay. Does that make sense? Okay. There you go. Good. Okay. So any other questions from the homework? Preferably out loud. Turn on the audio. Okay, so I'm going to take the silence. There's no more questions. Okay, so right. So last class, we talked about a few distributions, right? So last class, we talked about several important discrete distributions. Okay, and so this class, we are going to talk about sampling with and without replacement. We're also going to add to our list of important distributions by talking about the hypergeometric distribution. And we're going to, and then we're going to also talk about the Poisson distribution. Okay. And then if there's time, we're going to talk about Poisson processes. Okay. And if time, we're going to talk about, if time, we are going to talk about Poisson processes. Okay. All right, so let's get started. Talking about sampling with, looking at this first thing, sampling with replacement. So this is example 4.10. And so this is going to be titled sampling with replacement. I mean, at some point, but like not right now. Not right now. We're not going to use summation. But summations is used sometimes in the class. Okay, so okay, note. We use random sampling with replacement when the action of selecting the element at random from the set is repeated n times under the condition that each element in the set has equal probability of being selected. After the selection, the element selected is replaced with another element of the same kind. Okay, so we use random sampling with replacement when the action of selecting the element at random from the set is repeated n times under the condition that each element in the set has equal probability of being selected, and after the selection, the element selected is replaced with another element of the same kind. So once you choose something of equal probability, the next time you make a choice, it's reset. And so it's in a sense forgot the choice you previously made when you make the next choice. Okay. So here's the example. A box contains 10 red and 30 black balls. Use random sampling with replacement to obtain a sample size of 5 from the set of 40 balls in the box. Let capital X be the number of red balls in the sample. Find the probability function of capital X. Okay, so note that obtaining a sample size of 5 from the set of 40 balls means the problem is telling you that 5 balls are selected from the box. Okay, so it's telling you that you select 5 balls from the box that contains 10 red and 30 black balls, and X is the random variable that tells you the number of red balls in the sample. Okay, so every sample point of the sample space are 5 balls that you select from the box of 40 balls. So an input for X is one of the sample points of the sample space of this experiment, which was a choice of 5 balls from the box. And an output for X is the number of red balls in that sample point in the 5 that you chose. Okay, so X is a function where you input 5 balls that you select from the box, and then the output is the number of red balls in from those 5. Okay, so we want to find the probability function of X. Okay, so each selection of a ball is a Bernoulli trial in which success is getting a red ball and failure is not getting a red ball, or in this case, not getting a red ball means getting a black ball. Okay, so you select 5 balls. Now it's random sampling with replacement. So when you select the ball, that ball is then replaced when you make the next selection of the ball. Every time you select the ball, it's a Bernoulli trial, because you're either getting a red ball and succeeding, or not getting a red ball, getting a black one and failing. Okay. The probability of success then is, well, the probability of success is denoted by little p, right, which is the probability of success. And that's equal to the probability of selecting a red ball. And what is the probability of selecting a red ball? Well, every Bernoulli trial is the same. The probability is the same, and there's 10 red balls out of the total 40. And so that's 1/4, or as a decimal, it's 0.25. Okay, so P, the probability of success, is 0.25, and Q, which is denoted as the probability of failure, Q, which is the 1 minus P, is 1 minus 0.25, which is 0.75. Okay, so we now have the probability of success and the probability of failure, right? So Q is the probability of failure. And that's equal to 1 minus P, which is 1 minus 0.25, which is 0.75. Okay, so we have all of that information. Okay, so the goal is to find the it says find the probability function of x. The probability function of x is f of x, which equals the probability that capital X is equal to some fixed little x, where x are all the possible values of or all its possible values, right? But x is the number of red balls in the sample. You choose 5 balls from the box, so the number of red balls are either 0, 1, 2, 3, 4, or 5, right? If you choose 5 from the box, and there are a total of 10 red, right? So you could choose 5 red. So the number of possible, the possible values of x again are 0, 1, 2, 3, 4, or 5. Okay, so that's the goal, to find this, right? Find that. Okay, so let's do it. So let's find each probability. Okay, so let's find f of 0, which is equal to the probability that capital X equals 0. And so that's the probability of selecting 0, probability of choosing 5 balls from the box, and 1, and exactly 1 is exactly 0 is red. Okay. Okay, so here we're going to use the binomial probability function. And so let me remind you, right? We have b of x colon n comma p, right? And so, and this is equal to okay, so I'm just going to copy that. So let's do that again. Okay, so this is equal to n choose. This is equal to n choose x times times x to the p times n. Well, sorry, it's p to the x times q to the 1 minus x. Okay, you succeed x times, and the probability of success is p, so p to the x, and then you fail, probability of failure is q, and so if you succeed x times in n Bernoulli trials, you fail 1 minus x, n minus x times, so then you fail n minus x times. So that's the formula, and so we're going to use that formula. But first, we're just going to do the step of finding, what's the notation for the thing that gives us this probability, right? Okay, so the number of successes, right? Choosing a red is a success. So if you're saying exactly 0 red is in the sample of 5, then that means there are 0 successes. You're choosing 5, so there are 5 Bernoulli trials. And the probability of choosing a red, probability of success is 0.25. Let me say that again slower. Okay, so you choose 5 balls from the box, right? This is the probability that 0 of the 5 are red. That's 0 successes, 5 Bernoulli trials. The probability of success is 0.25. And so finding f of 0, finding the probability that x is 0, finding the probability of choosing 5 balls from the box and exactly 0 are red is b of 0, 5, 0.25. 0 successes and 5 Bernoulli trials where the probability of success is 0.25. And so now you can just use the formula, and the formula says that this is 5c0 times the probability of success, which is 0.25, raised to the number of successes, which is 0, times the probability of failure, 0.75, raised to the number of failures, which is 5. Because if you succeed 0 times, you fail every time. And there are 5 Bernoulli trials. Okay, and so you calculate that. So I do it as I guess I do it as a fraction here. I prefer fractions, so I have it as fractions. So I'm going to put this as fractions. Okay, so you have this, and then this is 243 divided by 1096. Okay. Okay, so now next we want to find f of 1, right? We know all the possible values of x. I wrote it here. So we start with 0, next is 1. We're going to do 2, 3, 4, and 5 after this one. This is the probability that x is equal to 1. And this is equal to the probability of choosing 5 balls from the box and exactly 1 is red. Okay? And that's equal to B of, and it's almost the same, except now it's 1 success in 5 Bernoulli trials with a probability of success of 0.25. And so now this is going to equal 5C1, and probability of success is 1/4. And so now it's 1 success, probability of failure is 3/4, and now there are 4 failures. And so you calculate that, and you get 405 divided by 1096. Okay, and we continue. And so you see that the only thing that's changing is one number, right? This is probability of x equaling to 2, and this is equal to the probability of choosing 5 balls from the box, and exactly 2 are red. So this is equal to the binomial probability function 2 colon 5 comma 0.25. 2 successes, 2 are red, right? It's equal to, good, okay. Then this is equal to 5C2. You choose 5 balls. How many ways to choose 2 of the 5 to be successes? 1/4 to the second power, 2 successes. 3/4 probably a failure raised to the third power. And then you calculate this product, and excuse me, you get 270 divided by 1096. Then you have f of 3, which is the probability of x equaling to 3. That's the probability of choosing 5 balls from the box, and exactly 3 are red. Okay, and this is equal to B of 3 colon 5 comma 0.25. 5 Bernoulli trials, 3 successes in 5 Bernoulli trials, and probability of success 0.25. And so this is 5 choose 3 times the probability of success, which is 1/4, raised to the third power, times the probability of failure, which is 3/4, raised to the second power. Okay, and you multiply all of that, you get 15 over 1096. Okay, and then f of 4, which is equal to the probability that x is equal to 4, which is equal to the probability of choosing 5 balls from the box, and exactly 4 red. And so this is equal to B of 4 successes in 5 Bernoulli trials with a probability of success of 0.25, and then this is equal to 5C4, number of ways to choose 4 out of the 5 to be successes, times 1/4 to the 4th power, times 3/4 raised to the 1st power. And so then you calculate this, and this is equal to wait, so let me check something. 0 is that, 1 is that, 2 is that, 3 is, this is 270. That was 270. Okay, and then 4 is 15 divided by 1096. That's 15 because you have 3 times 5 there. Okay, so, but it's not exactly that. Okay, so then f of 5 is probability that x is equal to 5. This is equal to the probability of choosing 5 balls from the box, and exactly 5 are red. Okay, and so that's equal to B of 5 successes and 5 Bernoulli trials where the probability of success is 0.25. And so that's equal to 5C5 times 1/4 the probability of success raised to the 5th power times 3/4 raised to the 0th power. Okay, and then that's equal to 1 over 1096. Okay, so those are the probabilities of each thing. Okay, so those are all the probabilities. Okay, and so that answers the question what the probability function is. And so just to write it out, f of x in this example is equal to, so we said, right, the probability is 243 over 1096. That's if x is equal to 0. Okay, the probability is 405 divided by 1096. That's if x is equal to 1. Probability is 270 over 1096 if x equals 2 or 3. And the probability was 15 divided by 1096 if x equals 4. So, yeah, if x equals 4, and 1 divided by 1096 if x equals 5. Okay, and so that is the probability. That is the probability function of x. Okay, so conclusion, the probability function of capital X is the following. This. All right? And so now we are done with that problem. Okay, any questions about this problem? This was the problem, right?
I have a question.
Yeah.
So you use the formula to get the values, like so how do you get, like, what are you, that's the formula. Okay.
Yeah, I mean, you know, you want to know what the formula means, right? So I don't want you to just plug into the formula, right? The formula means something, right? So this expression, right?
Yeah.
This expression, I'm going to label this as discussion, side discussion, right? When you're looking at this formula, right? What this is equal to is the probability that in n Bernoulli trials, the probability that in n Bernoulli trials you have is probably that in n Bernoulli trials with a chance of success in each trial of p the probability that in n Bernoulli trials with the chance of success in each trial of P, that you have exactly X successes. Okay? So this is the probability that in n Bernoulli trials with the chance of success in each trial of P, that you have exactly X successes, right? And so what's happening in the formula, right? What's happening in the formula is that this is the formula, right? But so ignoring this part for a second, right? Just focusing on this, right? Focusing on the bold part, right? So just focusing on, I'll answer the next questions after. Focusing on the bold part, right? P to the x times q to the n minus x would be, we have to copy this. This is the thing we're talking about. We'll go to the whiteboard. That doesn't look good. Okay, see, remember the thing I'm talking about, right? I'm talking, maybe write it down, right? So I'm talking about this and specifically this part, okay? Okay, I'm gonna go to the whiteboard. P to the x times q to the n minus x, right? So let's say you have n Bernoulli trials, right? And so let's say you succeed in the first X trials, right? Now I'm assigning an order to these trials. So in the first X trials, you succeed. And then in the next N minus X, ignore the number 3 here. Just X trials, you succeed each one. And then the remainder of them, there's a total of N. The N minus X remaining, you fail, right? So these are N minus X trials. And in each one you fail. So that's a Q, right? So you have Qs here, okay? The probability of succeeding in the first X trials and failing in the other N minus X trials is P to the X times Q to the N minus X. Each Bernoulli trial is an independent event. And so the probability of all of these things happening is the product of their respective probabilities. So the probability of succeeding in all the first X trials and failing in the first X trials and failing in the remaining n minus x trials is P to the x times Q to the n minus x. Does that make sense so far?
Yeah.
Okay, this is one ordering. If I took the same situation of succeeding in X trials and failing in N minus X trials, but I just changed the order of the success and failures, where, you know, I still have the same number of P's and the same number of Q's, except let's say I swap one of them. I put one of the Q and P, I just swap these two, right? If I swap those two, right, the probability is still P to the X times Q to the N minus X for that to happen, right? But this is a different situation because I've changed the order of my successes and failures, right? And so here, for P to the X times Q to the N minus X, you're finding the probability of one such ordering of X successes and N minus X failures in N Bernoulli trials. You then add, every time you have a new ordering, you add that probability, right? And so what you have is that the probability of exactly X successes is a sum of P to the X times Q to the N minus X. You just keep adding this thing, this quantity, over and over again, but you add it a certain number of times. And the number of times you add this quantity, P to the X times Q to the N minus X, is the number of ways that you can arrange X successes in a total of N trials. Does that make sense?
Yeah.
So this number, the number of elements in the sum, the number of terms in that sum, is the number of orderings of X, X trials. And it's the number of ways to choose X of the total N trials to be successes, N choose X. And so this is the sum of N choose X. This is the sum of N choose X terms. Each term is the same value. So this sum is equal to N choose X times P to the X times Q to the N minus X. Does that make more sense?
Yeah.
Okay. Each separate ordering the probability of any one such ordering of X successes in n Bernoulli trials, where the probability of success is P, any one such ordering has a chance of P to the X times Q to the N minus X chance of happening. Okay. And then to find the probability of exactly X successes, that means you could be any order, which means you have to keep adding P to the X times Q to the N minus X and choose X many times. And so the total sum is n choose X times P to the X times Q to the N minus X. Okay. Okay, so that's what's happening here. So the point of that was just to say, I don't want you to just blindly use the formula. I want you to understand what the formula means, right? If you understand what the formula means, not only will you understand probability better, it will be easier to do the problem if you understand the formula rather than just memorize it, right? Because if you understand something, it's easy to remember something that you understand, right? If you don't understand the formula, you're going to have to memorize something. And when you memorize something that doesn't make any sense, it's much harder to remember, right? If you understand the formula, then it should be very easy to remember it and use it.
Okay, thank you.
Okay, you're welcome. Okay, so now let's continue. So let's go to 4.5.4. This is on the hypergeometric distribution. Okay, so that's the definition. Oh, so there's another question. Oh, it's a review, right? So the review I said, right? So the class before the exam, right? So it's the exam is Thursday, right? So tomorrow I'll open the floor to questions that people have about the exam. Okay, so tomorrow. Okay, so I'll write that here, right? So important reminder. Okay, the review for test 1 is the day before the exam, is the class before the exam, which for test 1 is on Wednesday, July 28th during class. Okay. Okay. If people want, I'm willing to go on Blackboard Collaborate on Wednesday at some point. We can decide that today or tomorrow and to answer questions only if people want that and that they're going to come, right? Sometimes students say they do want something and I'm there and then nobody comes, right? So it's only if students are going to show up. Okay, so, and it's not going to be very long. Okay, so we'll talk about that at the end of class. So 4.5.4, the review is on Wednesday. The exam is on Thursday, right? So important reminder, test 1 is this Thursday, right? During class. Okay. Though the student who's taking the test in special services is doing it separate from the rest of class at the same time. Okay. During class, right? Use the normal Zoom link to attend. Normal class Zoom link to attend. Okay. If there's a problem with your Zoom link, you need to tell me before the day of the exam, right? But there shouldn't be because it's the same. If you're here, there shouldn't be any problem. Okay. So don't tell me 5 minutes before the exam starts that you can't get to the exam because there's a problem with your Zoom link. Okay, let's keep going. Okay, so 4.5.4, the hypergeometric distribution. So I think I answered your question about is on Thursday. You mean the exam is on Thursday? The test 1 is on Thursday. The review for test 1 is during class on Wednesday. Okay, the test is on Thursday. Yeah, good. Okay. If you have a question, say the whole question. Okay, don't say part of it. Okay, so that I know what. Okay, definition. Okay, a randomly selected subset of size n from a set with equal probability with every other subset of size n is called a sample of size n. Okay, so of size n, of size n, of size n. Okay, so let me read it. A randomly selected subset of size n from a set with equal probability with every other subset of size n is called a sample of size n. Okay, so that's the definition of a sample of size n. Okay, the reminders, I have the reminders here. I want them at the end of the class. So I'm just going to bring them down here. And at the end of class, it's going to be after the notes. Okay, but I don't want this underneath everything I'm writing. So I'm going to put space there. Okay. Okay, so example 4.11. Sampling without replacement. Okay, so a box contains N1 plus N2 items, of which N1 is of one type and N2 of a second. If a sample size n is selected from the box under sampling without replacement, and if capital X is the number of items of the first type in the sample, what is the probability function of capital X? Okay, so a box contains N1 plus N2 items, of which N1 is of one type and N2 is of a second. If a sample size n is selected from the box under sampling without replacement, meaning you don't replace things you select. So if you're choosing n things, you're selecting n things. Every time you choose something, when you make the next choice, the thing you chose is no longer there, right? And if x is the number of items of the first type in the sample, what is the probability function of x? Okay, so let's cut right to the chase. This is the probability function of x. Probability of capital X equals little x is equal to, so this is the expression. Good, okay, got it, okay. Okay, so in the numerator, we have N1, choose X, times N2, choose N minus X, and in the denominator you have N1 plus N2, choose N. If this is the probability function. Okay, so why is this probability function? What does it mean? Well, okay, so the probability that, so you have N1 plus N2 items, right? Let me actually copy this. Okay, write this down. Write this probability function down before I go to the whiteboard. Okay, so I'm going to move this to the whiteboard. Okay, let's go to the whiteboard. Okay, so you have a box. There's one box, a box. I want my box to be brown. Very particular about the details of my boxes. Okay, so this is the box, brown for box. And it's split into two separate sections. Okay, so there's two sections here. There's N1 items of one type. Okay, they're not pennies, but we used pennies before. And so I'm just going to say, I'm just going to use this for this is, so there's N1 of this type. This is type 1. And then for the second type, let's go with blue. And then there's N2 of another type of the box, right? They make up everything in the box. N1 plus N. A box contains N1 plus N2 items, of which N1 is of one type and N2 is of a second. And so we want the probability of probability function of X, right? We want the probability function of X. Probability the capital X takes on some fixed value, called little x. This is little x here. That's capital X. Just to really exaggerate it, I'm going to write the X really small. Okay, that's a fixed value of capital X, little x. Okay, so we have a numerator and denominator, right? The numerator is, well, if you're going to choose little x of the first type, well, there's a total of N1 things of the first type. And so you want the number of ways to choose little x of the things of the first type, right? So if I choose, you know, some of them I'm going to choose. So the ones I choose, I'm labeling as green, right? And so it's just the number of ways to choose a certain number of them of the total N1. So it's N1 choose X. The number is little x, right? Because little x is the number of items of the first type. That's little x. Little x is the number of items of the first type. Does N1 choose little x? Now, if I'm choosing N in total, little n in total, right? Then from N2, saying that I chose little x many of the first type and a total of n minus x means that I still choose n minus x more items, but they have to be of type 2 because I chose exactly little x of type 1. So choosing n in total and little x many of the first type means that I choose a remainder of n minus x from the second type. Okay, so n1 choose x times n2 choose n minus x. It's the number of ways to choose little x many of the first type and n minus x many of the second type. And that's divided by, well, there's a total of n1 plus n things in the box. And I want to choose a total, I'm choosing a total of little n many objects from the box. So the denominator is n1 plus n2 divided by little n, right? So what I'm doing is I'm considering all the ways I can choose little n many things from the box. And I want to know, right, the numerator is the number of ways that little x of them are of type 1 and n minus x of them are of type 2. Okay, so this is the probability function of x. Right, so the probability function of x, the thing we want to find, is this. Okay, that's called the hypergeometric distribution. Okay, the conditions on little x is that, and this is for integers, this is for integers little x, such that 0 is less or equal to x, less or equal to n, where n is the total number of things in the that you choose, and 0 is less or equal to little x, less or equal to capital N1. Okay, little x is a number of items of type 1. That has to be, that's at least 0, but it's at most the total number of things you choose from the box, right? You can't choose more things of type 1 than the number of total things you choose. Also, little x is at most N1, because if you choose little x items of type 1, and there are only N1 objects of type 1, you can't choose more items of type 1 than there are in the box. And so if there are N1 things of type 1, and you choose X of them, X has to be at most N1. Okay, so you have these two restrictions. It's technically 3 inequalities, because we're repeating X greater than 0 twice, but so there's 3 different inequalities here. Okay, and so we have these restrictions. Under these restrictions, you have this hypergeometric distribution. Questions? Okay, and so I'm going to put these conditions here. So the probability function is that for integers little x, such that those two inequalities hold the same inequality. So 0 is less or equal to little x, less or equal to n, and 0 is less or equal to x, less or equal to n1. Very good. So that's the hypergeometric function. So the probability function just discussed is called the hypergeometric probability function slash distribution with parameters little n, capital N1, and capital N2. Okay, so the next is definition 4.6. Let n N1 and N2 be positive integers. With n less or equal to N1 plus N2. The function h of x colon n comma N1 comma N2 is equal to that's equal to N1 choose x times N2 choose n minus x divided by N1 plus N2 choose little n. Okay, the parameters are little n, capital N1, capital N2, right? Because the function is determined by these 3 unknowns, okay? And so I'm just defining now this probability function. I'm using this notation to represent it, okay? The variables are n, little n, capital N1, capital N2, and then when you choose the value of little x, you're saying how many of them you're choosing of type 1, okay? And this is for integers little x such that 0 is less than or equal to x less or equal to n, and 0 is less or equal to x less or equal to n1. That is the hypergeometric probability function with parameters little n, n1, and n2. Okay, so that's the hypergeometric probability function with parameters little n, capital N1, and capital N2. Now, underline that so that this can be read easier. Okay, so that's that definition. Okay, so example 4.12, a carton of 24 hand grenades contains 4 that are defective. If 3 are randomly selected, what is the probability that exactly 2 of them are defective? Okay, so a carton of 24 hand grenades contains 4 that are defective. If 3 are randomly selected, what's the probability that exactly 2 of them are defective? Okay, so I'm going to put this also on the whiteboard. Let's see right here. Put this in black. Okay. The color might be good. Okay. So if we have a carton of 24 hand grenades. So carton, I might think of a carton as white, but white, you won't be able to see white. So I'm going to choose pink. Okay, so we have a carton is a box. All right, let's just go here. Okay, so you have 24 hand grenades. Let's choose red for hand grenade. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I've run out of room. 21, 22, 23, 24, 2, 4, 6, 8, 10, 12, 24. Okay, so you have 24 hand grenades in this box, right? And they contain 4 that are defective. So let's, maybe green would have been better. So how about this? 4 are defective. So I'm going to fill in 4 of them red to mean that the use of red means bad, right? So 4 are defective. And then green is going to be all the other ones that are not defective. So this is green for not defective. This is green for not defective. Green for not defective. Green for not defective. And we're just going to keep doing this another total of 18 times. Okay, so then this is also not defective. Not defective. Not defective. Not defective. Kind of has like a Christmassy feel because it's like green and red.
Yeah.
There we go.
I have a question.
Okay, so okay, so we have a total of 24. 4 are red for defective, and green is for not defective. 4 that are defective, right? So these are the 4 defective. Okay, if 3 are randomly selected, what is the probability exactly 2 of them are defective? Okay, so, right, we can see that these 4 are of type 1. I'm choosing the defective ones of type 1 because we want the probability exactly 2 of them are defective. So we care more about the defective ones than the non-defective ones. And then these other ones are of type 2, right? Kishan, you have a question?
Yeah, so the green one is not the green one is not defective, right?
Correct. Yep.
Oh, and the red one is defective.
Red are defective, yes. So these 4 are see the red underline? The 4 are defective, and then the other 20 are non-defective.
Okay.
Okay. So what I did was I chose type 1 to be the defective ones and type 2 to be the non-defective ones. So N1 has a value of 4 because there are 4 defective ones, and N2 has a value of 20, right? And so if there's a total of 24 hand grenades and 4 are defective, that means the remaining 20 are not defective, type 2. Okay, we want the probability that exactly 2 of them are defective. Well, X, I'm going to say capital X is X is going to be the number of defective, right, that you choose in this. But given the entire, not just the number of defective, the number of defective that you choose in this situation, right? So you choose 3 at random, right? And so capital X is that when you choose 3 of them, right? So let's say you choose 3 of them, right? X would be here. Here's the function X, right? Here's the random variable X. Let's say you choose 3 randomly, and say as one example of it, the 3 that you choose, are, you choose this one, and these 2 are defective. And you choose another one, and it's not defective, right? So you're choosing 3 randomly from the carton. And so let's say one such thing you could do is choose 2 defective, 1 that isn't. And so X, the random variable X, with that input would output a value of 2, because this choice of 3, right? You chose those 3, and then 2 of them are defective, right? So X is spitting out the number of defective for any choice of 3 in the box. So you want the probability that X will spit out a value of 2 as a random variable, right? Okay, so that's N1, which by the formula, right? So the formula, so look at your notes, right? The formula. So you have a total of 4 things that are defective. You want to choose 2 of them that are defective. So 4C2 is the number of ways to choose 2 of the 4 that are defective. And what has to happen is that of the remaining 20, if you chose 2 that were defective and you make a total of 3 choices, you have to choose 1 more that's not defective. And then you divide that by, well, we're really finding the probability. To find the probability that X spits out of 2, right? We're only considering cases where you choose 3 from the box. And so it's a total of 24 things in the box. That's 4 plus 20. So 4 plus 20, or 24, because there's a total of 24 things in the box. I'm just following the formula exactly. It's N1 plus N2 here, Cn. So it's 4 plus 20, there's 24 things in the box. C, choose 3 of them, right? Okay, and so that's there. And so that the value of that is the answer to the problem. Okay, and so when you calculate this number, when you calculate that, you get 0.0593. Okay, 0.0593. Okay, does that make sense? So that's the probability of If you choose 3 randomly from the box, it's a probability that 2 of them are defective. Okay, essentially, if I can make this easy, to remember this picture or have it in there, you have this carton, right? And so the probability that x equals 2 is like if you consider all the ways you could choose 3 balls from the carton, right? So you could choose 2 that are you could choose 3 that are bad, right? You could choose 2 that are bad and 1 that's good. 2 that are defective, 1 that isn't. But then there are a total of 4. There are a total of 4, right? So this is 1, 2, 3, right? And so let's say this is the first and second one. Let's say this is the first good one. And then, there's all the different ways that you could, let's say you choose. So you could also choose 3, but now instead of the first, second, and third defective, it could be the first, second, and fourth defective. And so you continue, right? And so then another way you could choose 3 balls from the box would be if 1 is defective, and 2 are not defective, right? But let's say the defective one was the third defective one, and let's say this is the second non-defective one, and this is the 7th non-defective one, right? And so the list continues, right? So there's lots of ways to choose 3 balls from the box, right? This number, right? This number of things, the number of ways to choose 3 things in the box, that's your denominator. That's n1 plus n2 choose 3. Okay, that's the number of ways to choose 3 balls from the box, right? And you could have different amounts of in each choice. You have a different number of defective hand grenades, right? But the numerator is saying, okay, I only want to count all the ways in which 2 of them are exactly 2 of them are defective, right? So this one has exactly 2 defective. So this one would be in this count, right? Because you had 2 defective, 1 non-defective. And in this case, you had 1, 2, and this was the first, non-defective one. So you would have this one there. These 3 would not be in this count because none of the other 3 have 2 that are defective. There's other ones I didn't list, right? You could have 2 that are defective and 1 non-defective, right? But when you make this choice, the choice is you choose different ones. So let's say this was the first defective and the second defective one, but instead the first non-defective was the 7th non-defective one, right? And then you could choose 2 that are defective, 1 that's non-defective. But this could be the second defective, this could be the 4th defective, this could be the 9th non-defective, right? And so this list would also continue. And so you would count the number of ways that in of the ones of the first type that you chose X that were defective, and then of the second type, which are the non-defective ones, you chose N minus X non-defective ones, right? And so this count, this product, N1 choose X times N2 choose N minus X, it's counting all the ways in which you choose 2 that are defective and 1 that isn't. For this example, the X would be, right? So for this example, this would be, there are 4 that are defective. You're choosing 2 of them of the 4, and then times 20 that are non-defective. You're choosing 4 minus, wait, there's 3. We're choosing 3 here. So you choose 2 out of the 3. 2 out of the 3 are defective times 20 times times 20C1, there's 20 that are, well, I was right the first time. There are 4 that are defective. You're choosing 2 of the 4 to be defective, and you're choosing 1 of the 20 that are non-defective. So you're choosing, there's 2 defectives, 1 non-defective. So this product is counting all the ways in which you could, given that you're choosing 3, this is the number of ways that exactly 2 of them are defective, and this is all the ways in which you could choose 3. And so the probability that given you choose 3, that exactly 2 are defective is this number divided by that number. So it's this 4C2 times 20C1 divided by N1 plus N2, choose N, right? N is the number you choose. So in this case, this is 4 plus 20. This is a total of 24. In the carton, 4 defective, 20 aren't, and you're choosing exactly 3 of them. So in this case, this is 24C3. It's the number of ways to choose 3 of the 24, right? All the ways to choose 3 out of 24. That's the denominator. But then the numerator is the number of ways that exactly, given that you choose 3, right, that 2 are defective and 1 isn't. So it's this quantity divided by this one, right? Your sample space are all the ways to choose 3. And then the event, is thinking of exactly 2 of them are defective. Okay? Okay, so hopefully that helps you visualize how, we get this divided by this in this example. Okay, so let's go back to the whiteboard. Okay, so the solution is illustrated and done on the whiteboard. Just another example. Example 4.13. From a group of 15 chess players, 8 are selected. What is the probability 8 selected include 3 of the 4 best players in the group? Okay, so solution is solution, the goal is to use the hypergeometric probability distribution, which is the hypergeometric distribution, to solve the problem. Okay, the formula is this. That's the formula. So to use the formula / solve the problem, you can ask yourself these questions. In a sense, these are the steps, right? So the first question you can ask yourself is, what is, how many total how many objects of type 1 are there? Denote that quantity by N1. 2, how many objects of type 2 are there? Denote that quantity by N2. Okay. Okay. 3, how many objects from type 1 are you selecting? Denote that quantity by little x. Or how many objects are you selecting in total? Denote that quantity by little n. Okay, so you see that this formula uses these four variables, n, capital N1, capital N2, little x, and little n. And so just ask these four questions to get the corresponding four values, and then you just plug them in, okay, into this expression, and you're done. Now, I still want you to understand the formula, which is why in the carton example I gave earlier, I'm illustrating for you what's happening here so that you can understand, visualize what's happening when you're doing this formula, what it means, right? Okay. I also did that here, right? So I gave two illustrations that's familiar. This is an illustration, and this is of hypergeometric probability function. So I don't want you to just know the formula. I want you to understand it. Okay. But in any case, you ask these four questions, and you can get the corresponding four values, x, n, n1, n2. Okay. So the answers to these questions are, answers to those questions are, so for the first one, how many objects of type 1 are there? Actually, I need to ask zero. Question 0 before question 1. What are the objects of type 1 and of type 2? Okay, let's do that. Okay, let's ask that question also. Okay, so 1 through 4 give you the values. Question 0 prepares you for that. Okay, so from a group of 15 chess players, 8 are selected. What is the probability 8 selected include 3 of the 4 best players in the group? Now I'm going to go to the whiteboard again. Okay, so and there's the question. From a group of 15 chess players, 8 are selected. Was probably 8 selected include 3 of the 4 best players in the group? Okay, I'm going to use a box again. Okay, there are 15 chess players. So I'm going to denote the chess players by each chess player is going to be a circle. Okay, and it's going to be a brown circle. So we have 4 circles. Now 6. Now 8. Don't have me draw people. They'll be stick figures. They'll be terrible. So it'll be 5, 6, 12, 13, 14, and 15. Okay, so we have 15 chess players represented by circles. Okay, we want to select 8 of them, right? But was the probably 8 select include 3 of the 4 best players in the group? So what color denotes like, let's go blue. Okay, so the 4 best players in the group, I'm going to denote them by blue. Okay, and I'm not even going to say which is the first, second, third, or fourth. They're just the 4 best. Okay, so dark blue is like the color of royalty. So we're going to go with dark blue. Okay, so we have 4. These are the 4 best players in the group. And then everyone else isn't as good. And I'm going to choose orange. This is my least favorite color. I'm going to choose orange as the remaining ones. And these are met colors now. And so now we have all the other chess players aren't as good. They're not the 4 best. Sorry. There. Okay. So, okay, 4 best, everybody else. Okay, so, all right, so those probably 8 select include 3 of the 4 best. So, type 1 is going to be the best players, right? So this is type 1. So N1 is going to be 4. See that? There's 4. There's four play of the. You have type 1, which are the 4 best players, and the number of the 4 best players is 4, right? And then N2 is everyone else of type 2, which are not the 4 best players. If there's 15 in total, that means N2 is a value of 11. Okay, so we've answered what N1 and N2 are. Okay, so let me go back here. So okay, so type 1 consists of the 4 best players. Type 2 consists of the other 11 players that are not among the top 4. Okay, question 1, how many objects type 1 are there? So we answered that on the whiteboard, and 1 is equal to 4. Right, the 4 best players, the number is 4. How many objects type 2 are there? Type 2 are the old number of all the other players. It's 11 because it's a total of 15. Question 3, how many objects from type 1 are you selecting? It says, what is the probably 8 selected include 3 of the 4 best players? And so little x is going to equal 3. We're selecting 3 of the 4 best players. 3 are from type 1. Okay, so we're selecting 3 from type 1. So I'm going to denote that by a check. So we're choosing 3 from type 1, right? So little x is 3. Choosing 3 of the 4 best players. Little x is 3. And then the 4th question, how many objects are you selecting in total? Was it probably 8 selected include? So 8 selected. We're choosing 8 in total. Denote that quantity by little n. So little n is equal to 8. Right? And so now we're just going to use this formula. There's the formula. But we're going to plug in x is 3. So little x is 3. Little x is 3. Which battery I have 19% remaining. Little x is 3. Little n is 8. So I'm just plugging in the values for everything. N1 is 4. And N2 is 11. Okay, so we now have that. That's the probability we want to find, right? It said, what is the probability 8 selected include 3 of the 4 best players in the group, right? So that's what we want to find. You wouldn't necessarily have to even write this, but I'm writing it just to help you understand it. What is the probability that 8 selected include 3 of the 4 best players in the group? It's equal to that, which is equal to that. Okay, and so now that's equal to, you have this quantity here. 4C3 times 11C, 8 minus 3 is 5. And 4 plus 11 is 15. So now I'm just doing the addition here, right? So, yeah. So now it's just, we have this, and then you calculate that. And the value you get is that's equal to 0.287. Okay, and then you're done. Okay, now going back to the whiteboard with the pictures I drew here, right? Keep in mind the problem is telling you that little n is equal to 8. So you're choosing 8 in total, right? 8 are selected. The 8 are selected is telling you that n equals 8, right? Okay, so I'm just going to undo the circling though. Okay, so the n equals 8. Now, just to rewrite here underneath the picture, right? The probability that x is equal to 3. This is little x, that's not capital X. It's saying probably capital X equals little x, where little x equals 3. So that means that capital X equals 3. So probably that you choose 3 of the 4 best players, right? Again, are there's 4 best players. You want to choose 3 out of the 4. There's remaining 11 players that are not the best. And if you choose 8 in total, and then you've chosen 3 that are the best, you're choosing 5 that are not the best. So you choose 3 out of the 4 of the best and 5 out of the 11 that aren't. And you divide that by, well, you chose a total of 8 things, but it's out of the total 24 total 15 players. So that's divided by 15, C8. Okay, and so that's right, and so that's that, and then you compute it, right? And we got the number before. I don't want to write the number here because I want you to, the point here is to visualize how this quantity, this fraction, numerator and denominator, is expressing what's happening in this problem. Okay. Okay, so that's that problem. So let's go back to the whiteboard. I mean, go back to the Word. Okay, so we're going to talk about the Poisson distribution another time. Okay, so we're going to stop here. And yeah,
You received the whiteboard.
oh, thank you. You're right. Thank you. Good. Okay, good. Okay, so then we'll stop there. So keep in mind, before you go, remember that the review for test 1 is tomorrow, right? The review for test 1 is going to be tomorrow, and the test 1 is this Thursday, right, during class. Okay, if you're not sure about how, I went through everything about how to take the exam. If you go to Blackboard, you should see Blackboard on the screen now. Here's the main screen. It looks pretty much like this for you. If you go to tests, here's this. There's rules for exam and what to do to take online exams. So you should read both these things. It's reiterating most of what I said during class when I explained about exams. But read these two so that way you know everything you need to know. It'll tell you what to do to prepare. And remember, this test 1 folder are the materials for your practice for test 1. So these are practice questions for test 1, and these are the answers, right? Don't look at the answers until you do the practice questions. We've covered all the material for the exam 1, right? And the syllabus is what reminds you what's on the exam, right? So if you click the syllabus and you open it, so I clicked the syllabus button. So I think you saw that. I'm going to go to the syllabus now. Maybe you can already see the syllabus. I'm not sure. Okay, so right here's the syllabus, right? Chapter 1, test 1. Chapter 2, test 1. Chapter 3, test 1. Everything else is test 2, right? So it's these first 3 chapters that are on test 1, okay? There's 2 tests, test 1, test 2. They're each 30% of your grade. The final is 40%. For the first test is 30% of your final grade, okay? Okay, so that covers all of that. Okay, so I'll see you tomorrow, and we'll have a review tomorrow. And remember, the test is Thursday. Kishan, you have a question or no?
No.
No?
No.
Okay, you don't. Okay, I think you said don't. Okay, so I'll see all of you tomorrow. Okay, bye.